Hello, everybody. I'm Mohsen Banaei from Technical University of Denmark. I would love to be there to present the paper in person, but unfortunately, for some reason, I couldn't manage it. So I'm just recording this video, and I hope it would be useful for everybody. So this paper is about proposing a digital platform for power-to-X plants and facilitating their participation in the electricity markets and also using their waste heat for different purposes, for district heating or like the buildings around the power-to-X plants. This work is a kind of a teamwork. Different people with different expertise work on it. And I was mostly focused on the algorithm development, but I would try to do my best to provide you all the technical information that is necessary for this particular paper. So I would continue my presentation by providing an introduction and defining our contributions, discussing about the aspects of the power plant or energy system that is covered by this operational digital platform or ODP using the smart grid architecture model, SGAM, and then I will go through the modeling and then will provide you some of the development results and eventually I will conclude the paper. So as an introduction, you know that there is an increasing attention on demand side flexibility. It means that there is an increased need on the demand side of the energy system, like energy consumers, to participate in supporting the grid by providing flexibility. And by flexibility, we mean the capability of reducing or increasing the energy consumption on the demand side of the system to support the grid. And power-to-X plants are very reliable source of flexibility. Their scale is big enough to provide significant amount of flexibility. And they have some characteristics that makes them very suitable for these purposes. But on the other hand, we need to make some development in the services and provide new solutions, hardware and software solutions, to make the participation of these P2X plants in demand-side flexibility services easier. And for this purpose, we need some scalable and interoperable solutions. What we develop here as an operational digital platform is to respond to this need. By operational digital platform, we mean a physical and virtual information and communication technology resources that operates via communication infrastructure to support the flow, storage, and process and analysis of the cross-sector data. These sectors could be electricity, heat, or even other sectors, including mobility. And for this specific paper, our focus would be on the data centers, electrolysers, and heat pumps as power-to-X systems. Here you can see an overview of the concept of the ODP. So at the bottom layer, you can see the electricity grid that supplies the power-to-X plants. That could be like the data center here and also the electrolyzer. So we need to manage these plants in an optimal way to optimize their energy consumption and also use their waste heat through the heat pumps or heat exchanger for supplying the heat demand of the buildings. But to do this, we developed this ODP that allows us to interact with these power-to-X plants, model them, analyze them, and then estimate how much is their energy demand for the next day, submitted to the existing markets like the day-ahead market, and also evaluate how flexible they are next day to increase or reduce their consumption, and then also submit another bid to another market for providing balancing services for the power system. This provides like a an extra revenue stream for these plants, and also considering the waste heat that is used by buildings, there would be another revenue stream for these plants. So overall, we are thinking to benefit grid and end user, and also the power to X plants owners. So with this paper, our goal is to develop an ODP which is scalable and interoperable, allows the power to X plants to participate in the day-ahead market, facilitate to provide the provision of flexibility from power to X plants, and also use the waste heat of these plants for supplying the heat demand. Now we wanted to have a look into the energy system and see what domains and zones of energy system is affected by this ODP. So here you can see a standard architecture or diagram of the SGAM, a smart grid architecture model. And then with red blocks, you can see the domains and zones that are touched by the ODP. So when it comes to the process, field, and the station, we would work on the domains of the heat, power to X plants, and waste heat reuse. So we will not have focus on the power generation side. And also when it comes to the operation and enterprise, our focus would be on just the power to X plants. So when we talk about the business logic and the operation, our focus would be on the power to X plant, and we ignore the heating system. And then when it comes to the market, our focus would be on the day-ahead market and balancing market, which are mostly about the generation, transmission, and distribution side of the system. But as you can see here, we need to analyze this platform at different layers of the system: the component, communication, information, function, and business layer. And the platform touches all these layers at different levels. In the component layer, we would focus on the data center, electrolyzer, and heat pump, and waste heat reuse systems, sensors, and meters. In the communication layer, we would work on the communication between the platform and market, platform and the plants, and platform and the plants and the grid and district heating system. With the information layer, we would work on the data from the sensors and meters, the bids submitted to the markets, what we receive from the markets, and also the prices and powers that accepted for these plants from the market. And the function would be focused on the functionality of these plants, the models, the optimization, and participation in the market. And the business layer also, as I mentioned before, would be focused on the business logic of the power to X plant. So to have this ODP work, we need some power to X plants. So first, the ODP need to interact with the plants, but we couldn't connect our ODP to the real system. So we developed some emulators of the plants on the Modelica, but also we put them on the Raspberry Pis to represent the real system. And we did this for data center, for electrolyzer, and also for the heat pumps. So this represent the systems outside the ODP that we interact with. But we also need to model these systems inside the ODP, because if we wanted to estimate their energy consumption, we need to have a mathematical model of all these technologies and estimate their energy demand, like the temperature references, all the restrictions, estimate their energy consumption to bid for the next day. So we would have two modeling stages. One modeling is to emulate the device outside the platform that platform interact with, and another modeling step that is inside the platform to estimate their energy consumption and flexibility to bid into the markets. So here you can see in some slides the model we use in Modelica to emulate the data center. Next one is about the electrolyzer, and also here about the heat pumps. Then we needed we need to interact with the day-ahead market and also the balancing market, but we couldn't also connect our platform to the real market. So we also simulated the day-ahead market and also the balancing market. The day-ahead market was simulated by an optimization problem, very well-known optimization problem in power system that receives the beats of energy consumption and also generation from all the producers and consumers, including our ODP, and also determines the accepted power to consume next day and also the price of the electricity for each hour. So that's what this part of the paper is focused on. The next part is about the balancing market. So after participating in the day-ahead market, the platform can submit the bids into the balancing market and say, okay, based on what is determined in the day-ahead market as the baseline, how flexible I am next day to support the grid when it comes to the power imbalance, because it's very critical to keep the power system in balance. And in this case, we focus on two systems, two balancing services. We call them the FCRN and FCRD. When we talk about FCRN, it means that our platform is going to react on any deviation in the frequency in the system. So you can see here on the left side that when the frequency deviates on both sides, we activate our flexibility in a proportional way. But on FCRD, we have a dead band. So we don't activate flexibility as long as the deviation in the frequency is 0.1 hertz. But when it gets greater than 0.1 hertz, then we would react accordingly. So we are simulating also this market and also how, as a service inside the platform, how to react to the frequency deviations. Here you can see a list of the solution services we develop in our ODP. We have modeling services, as I mentioned before. We have power-to-X optimization to estimate the energy consumption for the next day, day-ahead market bidding, flexibility market bidding, flexibility procurement, so how to procure flexibility from the different plants, and also actuation service, how to send the actuation signal to each plant. Here in this figure, you can see the SGAM prototype design for our platform. So we have the ODP as the core, and we have the flexibility bidder in all markets. We have the FMI that run the simulation and optimization models. We have the aggregator that aggregates the bids, submit them into the market, and also disaggregate the flexibility bid among all the resources, all the P2X plants, and also the gateways for communication. We have the market clearing platform for bidding, bidding into the day-ahead market, clearing the market, and returning the prices and accepted power. One of the features that we define for our ODP, that if you can see here in a screenshot, that for each type of the technology, we can insert different parameters, and then based on these parameters, we can simulate or estimate how much would be the energy consumption next day, and this is what we can bid into the market. But also, we allow, or we define this possibility or functionality that allows the plant owner to modify this curve and make some adjustment. Or they can even just submit a totally different curve based on their prediction if they don't have these parameters. So it's quite flexible. And then at the bottom layer, we have the plants emulators and also the grid emulators, the heat grid and also the electric grid. So we put the models of the power-to-X plant on Raspberry Pis that emulate the real plants, and the ODP can interact with these plants. And also we have models the district heating and power network with RTOS-based transducers. Here you can see some of our results on frequency response. So at top you can see how the frequency fluctuates, and at the bottom you can see on the left side, you can see how the data center responds, and the right side, how the electrolyzer responds. And as you can see here, if you remember from the FCRD service, there was a dead band. And that dead band means that we don't need to activate the frequency response at all time intervals. So the deviations in the consumption from the baseline is not significant when it comes to the FCRD, the orange curve. But when it comes to the FCRN service, there are a lot of fluctuations in the base from the baseline, because we need to keep respond to the frequency deviations. And similarly for the heat pumps, you can see that we have the baseline, but there are a lot of fluctuations around it to respond the frequency service. So the baseline, the orange one, represent what we get or what we offer to the day-ahead market, but the blue one is mostly is considered the baseline plus the FCRN service. And also here you see the how the temperature in the different plants changes, the heat pumps, the electrolyzer, and the data center. The data center and electrolyzer has a higher inertia, so there are not significant fluctuations in the temperature. But the heat pumps, they don't have a high inertia, so the temperature changes frequently. And this temperature is what we mean about supplying the heating system. So this outlet heat is used by the heat exchangers or the heat pumps to provide some heating or to supply the heat demand of the buildings or also district heating. So this was my presentation. As a conclusion, as we discussed before, so we propose an ODP for power-to-X plants to participate in the day-ahead market, in balancing market, to provide some services for the heating system and also the electrical system. We listed a variety of services, we developed them, and we implemented them in our ODP. We provide some hardware interloop emulators for data centers and electrolyzers and heat pumps. We simulated the market, we simulated the technology, the power-to-X plant inside the ODP, and we could see that the ODP could manage the participation in the market, providing balancing service and also supplying the heat demand successfully. For the future, we are planning to extend what we did before to include the larger scale power-to-X plants, the ones that with legacy systems, and try to interact with those systems as well. Thank you very much for your attention. If you have any questions, you can contact us. You have our contact email addresses here, so don't hesitate to call us or send us an email. Thank you so much.